Welcome back to Arxflix. Today, we're diving into a groundbreaking paper titled SpatialVLM, Endowing Vision Language Models with Spatial Reasoning Capabilities. This research tackles the challenge of equipping vision language models, VLMs, with the ability to understand and reason about spatial relationships, a crucial skill for tasks like visual question answering, VQA, and robotics. This figure showcases SpatialVLM, a system that enhances VLM's spatial reasoning capabilities. It demonstrates the model's ability to estimate metric distances from 2D images, addressing a key limitation of current state-of-the-art VLMs. While VLMs have achieved impressive results in various tasks, they often struggle with spatial reasoning. They lack the ability to understand the positions of objects in 3D space and their relationships, like distances or size differences. The authors hypothesize that this limitation stems from the lack of 3D spatial knowledge in the training data. Most VLMs are trained on image caption pairs, which contain limited spatial information. To address this, SpatialVLM introduces a novel data synthesis and pre-training mechanism. It leverages off-the-shelf vision models to automatically generate a massive dataset of spatial reasoning questions and answers. This figure outlines the data synthesis pipeline. It starts with real-world images, extracts object-centric information using vision models, and then synthesizes spatial VQA data. The pipeline involves several key steps: semantic filtering to select suitable images, object-centric context extraction, lifting 2D contexts to 3D, ambiguity resolution, and finally, generating spatial VQA data. SpatialVLM is trained on this generated dataset, enabling it to learn direct spatial reasoning capabilities. This means it can answer spatial questions without relying on external tools or other models. The authors also explore chain-of-thought spatial reasoning, where SpatialVLM is combined with a powerful large language model, LLM, to solve complex spatial reasoning tasks. The LLM breaks down complex questions into simpler ones, queries SpatialVLM for visual information, and then combines the reasoning to arrive at an answer. This figure illustrates chain-of-thought spatial reasoning. The LLM acts as a coordinator, breaking down a complex question and using SpatialVLM to answer simpler spatial queries. The paper presents extensive experiments to evaluate SpatialVLM's performance. They compare it to various state-of-the-art VLMs, including GPT-4, Poly, and PaLM. The results show that SpatialVLM significantly outperforms these baselines in both qualitative and quantitative spatial VQA tasks. It demonstrates a remarkable ability to answer spatial questions, including those requiring metric distance estimations. The authors also investigate the impact of different training strategies, such as freezing or unfreezing the visual encoder, and the effect of noisy data on the model's performance. SpatialVLM's enhanced spatial reasoning capabilities unlock exciting new applications, particularly in robotics. It can serve as a dense reward annotator, providing feedback for robots based on their actions and spatial relationships. This figure shows SpatialVLM being used as a reward generator for a robotic manipulation task. The model provides a reward based on the distance between the robot's gripper and the target object. Overall, SpatialVLM represents a significant advancement in the field of vision language modeling. It demonstrates the importance of training data for spatial reasoning and opens up exciting possibilities for future research and applications. Thanks for watching Arxflix. Don't forget to like, subscribe, and share this video with your fellow researchers. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.